In today's video, we're going to continue our discussion of stereochemistry. We've already seen that cycloalkanes can have more than one isomer. So, for example, cyclobutane, 1,2-dimethyl or 1,3-dimethyl cyclobutane has two isomers. The cis isomer and the trans isomer. Alkenes can also have cis and trans isomers. So if we think about butene, the two methyl groups can either be on opposite sides of the double bond in this case, or on the same side of the double bond in this case. And so this molecule is trans to butene, whereas this molecule is cis to butene. Chirality is a property of three-dimensional objects that many molecules have. A chiral object is an object that is non-superimposable with its mirror image. Consider, for example, your left and right hands. They're mirror images of one another, but I can't put one on top of the other. My thumbs don't overlap. I could turn them sideways and clap them together, but now the front of my hand is lined up with the back of my left hand, and so these are non-superimposable mirror images of one another, and so your hands are chiral. Have you ever tried putting your left foot in a right shoe? It doesn't work well because your left foot and your right foot take up different spaces, and so just like your hands, your feet are also chiral. There are also some molecular examples that we should talk about, and I'm going to start with alanine, the simplest chiral amino acid. Amino acids are the building blocks of proteins, and alanine is one of the ones that shows up regularly in the human proteome. They're called amino acids because they have both an amine functional group and a carboxylic acid functional group. This is alanine. It's L-alanine because it has a non-superimposable mirror image. We draw the mirror image of this molecule. This is D-alanine. L-alanine is the amino acid that's usually incorporated into proteins, and D-alanine is not. If you were to try and superimpose D-alanine on top of L-alanine, it wouldn't work. If I make a copy of this and drag it over, notice my methyl groups don't line up, the amine doesn't line up, and the carboxylic acid doesn't line up. If I were to redraw this, so I rotated it 180 degrees about this CH bond, that's going to put my methyl group over here. But the carboxylic acid comes to the front. and the amine group goes to the back. So again, if I try and superimpose this on my starting material, I can line up the methyl groups in the CH, but the carboxylic acid and the amine are not the same spot. And so this object, or this molecule, alanine, is chiral because it's non-superimposable with its mirror image. I get rid of the extra copies of alanine. L-alanine and D-alanine are said to be enantiomers of one another. Enantiomers are just two molecules that are non-superimposable mirror images. Two molecules that are enantiomers of one another have all the same physical properties except one. They have the same boiling point, they have the same melting point, they have the same physical appearance, they have the same solubility. But they have a weird property in that they rotate plane polarized light, and they rotate it in opposite directions. Light is a transverse wave, and so it travels through space like this. If we were to look at this light coming at us head on, so if I'm going to look at light that way, we would have some of the light that is bouncing up and down like this, but other versions of that wave are going back and forth. Some are going diagonal, and so the light is bouncing up and down in its wave all sorts of different ways. We can filter that through a polarizing filter, and your sunglasses often are an example of this. If we put that through a polarizing filter, we can filter out all of the light except light that's traveling in one particular direction, and so in this case, up and down. So if we put that light through a polarizing filter, like this, and we get it so that it is polarized in one direction, and then we were to pass that light through a sample that contains only one enantiomer of a chiral molecule, that sample would rotate that plane polarized light so that it's now coming out in some rotation away from where it was. And so in this picture, this sample has rotated plane polarized light approximately 30 degrees clockwise. If this sample that we passed it through was one enantiomer, so let's say it was the D enantiomer of alanine, the L enantiomer is going to rotate light the opposite direction. It's going to rotate it approximately 30 degrees counterclockwise. An object is said to be achiral if it is superimposable with its mirror image. There are lots of different examples of this. A spoon, nitrile gloves from lab are both superimposable with their mirror images. We think about a molecular example, 2-bromo-2-chloropropane. We might draw that like this. So this would be carbon 1, 2, 3. That's 2-bromo, 2-chloropropane. This has a mirror image. It looks like this. And while if I copy this and tried to bring it over directly, they don't line up. If I were to rotate this molecule 180 degrees that way, then we put bromine over here, chlorine over here, I would have a methyl group there and a methyl group there. And if I try to superimpose this blue version over this green version, those match up perfectly. And so that is an achiral object. Carbons of chiral objects often have 4 different substituents on them. So if we look back at alanine, that had hydrogen coming up top, a methyl group, then amine, and a carboxylic acid. This carbon has 1, 2, 3, 4 different groups attached to it. A carbon with 4 different groups is an asymmetric carbon or asymmetric center. Most molecules that have an asymmetric carbon are chiral, and most molecules that do not have an asymmetric carbon are achiral. So if we look at 2-bromo, 2-chloropropane, the carbon in the center here only has 1, 2, 3 different groups, because this group here and here are both methyl groups. If 2 of the substituents on a carbon are the same, often its mirror image is going to be superimposable with itself. I want to give you some gross generalizations and probably provide a couple of counterexamples here and there. But in general, a compound without any asymmetric carbons is going to be achiral. An exception to this rule is something called an alene. An alene looks like this. This dot here represents a carbon. That carbon is sp hybridized because it's participating in 2 different double bonds. The way the p orbitals form these bonds, it is necessary that if the 2 groups on this side of the molecule are in the plane of the page, the 2 groups on this side of the molecule are coming into and out of the page, or they're perpendicular to the plane of the page. This molecule, despite the fact that it doesn't have any asymmetric carbons, is chiral. If I draw the mirror image of this molecule, get a methyl group coming out, hydrogen going back, a methyl group going down and a hydrogen going up. Those two molecules are different. If I were to spin this molecule 180 degrees, I would get this. That methyl group would be going into the back, and that hydrogen would be coming out of the page. So that hydrogen is here. That methyl group is here. If I try and superimpose this on my structure up here, notice that I can get the hydrogen and the methyl group to align on the left, but the methyl group is in the back rather than in the front. And so those two molecules are not superimposable. And so an alanine does not have an asymmetric carbon, but it is or can be a chiral molecule. A compound with an odd number of asymmetric carbons is always chiral. There are no exceptions to that rule. A compound with an even number of asymmetric carbons is sometimes, or maybe even usually, chiral. But there are a few, or there is a counterexample to this. Let's consider this structure. In this molecule, both this carbon and this carbon are asymmetric. They have 1, 2, 3, 4 different groups attached to it. And so if a carbon has 4 different groups, it's asymmetric. If I think about drawing the mirror image of this, looks something like that. If I try and superimpose this, you'll notice that they line up perfectly. And so this molecule, despite the fact that it has a couple of asymmetric carbons, is not chiral. And it's because it has what's called an internal mirror plane. Right? If I reflect across this plane, this methyl group winds up on top of that methyl group, this hydrogen winds up on top of that hydrogen, and this carbon winds up on that carbon. And so that's called an internal mirror plane, and any molecule that has an internal mirror plane is not going to be chiral. This structure is called a mesostructure because it has an asymmetric carbon, but it is not chiral. So the ultimate test for chirality is it superimposable with its mirror image? If it is not superimposable with its mirror image, it is chiral. If it is achiral.